PhD student here in the Department of Physics and Astronomy at Northwestern, and I study the stability of complex networks. So networks are everywhere, be it a network of professionals across the globe, let's say researchers, or be it the gigantic power grid on the continental United States or any other country for that matter, or even a flock of birds that makes these amazing formations and travel thousands of miles with great accuracy. So networks are present on all scales and all walks of life, let it be nature, technology, or human interactions. But mathematically, a network is just a large system with many components that interact with each other. So we can represent all of these networks as a bunch of dots connected with lines, where the dots are the components of the network and the lines are the interactions between them. Because we can mathematically represent them like this, we can also study a large plethora of networks with similar mathematical tools. Think of a wheel. A wheel is used in vehicles, skateboards, in our watches as gears, or in any machines that have moving parts. But every time we come up with a new application of a wheel, we don't reinvent the wheel. Instead, we take the concept and we apply it to different applications. In the same sense, we use the same tools of network science to study all of these different networks and understand how they work. So we use this mathematical framework and make some assumptions about what we understand of the system to create a network model and see whether it behaves similar to what we observe in nature. If not, we update the model and try to get closer to what we observe in nature. So if you ask me what's one of the most important structural properties of networks, I would say it's their complexity. By complexity, I mean how large the network is, how many components it has, and how highly connected it is. And one of the most important behavioral properties of the networks is their stability, which means if given a disturbance, how fast can a network recover from it and come back to its original state. Take the example of the flock of birds. If one bird strays away, that does not cause the whole formation to break down. Instead, the bird communicates with the rest of the birds, finds its way back, and the formation is still intact. That means this network is stable. So, our current models of network science predict that as the complexity of a network increases, the network actually grows more and more unstable. At the first glance, this seems pretty intuitive, right? Because the more the number of components and the more the number of edges, the more there is a chance of something going wrong, right? But on the other hand, in nature, we observe a lot of networks which are large, complex, and yet remarkably stable. The best example of this would be the food web, where a lot of predators and prey interact with each other by many mechanisms and maintain their stability. So how does nature do this? Clearly, there's a gap between what we understand and encode in our network models and what we observe in nature. This is termed as the complexity-stability paradox, and this is something I try to shed more light on through my research. So there are many ways to approach this problem. The answer to this might hide in many aspects of networks. One of them could be the structure of the networks. The structures of networks could be ordered or completely disordered. When I say ordered networks, I mean there is an obvious pattern as to how the network nodes interact with each other and are connected with each other, as opposed to completely disordered networks, which we cannot discern any patterns in the first glance. And there can be any amount of order between these two extremes of completely ordered and completely disordered networks. The current models of network science that we use to predict the complexity-stability relationship assume that the network structures are disordered, but that may not be true. Maybe the food web has some structure to them that gives them the stability. So maybe part of the answer lies in the structure of the networks. Or it could be how strong and what kinds of interactions the network has. So in a food web, not all interactions between species are the same. The way a predator and a prey interact with each other is not the same as how two species that compete for the same resource would interact with each other. So maybe it's the diversity of interactions in the network that affects the network stability. Currently, even this is assumed to be completely disordered in the current network models, and we need to learn more as to how the interactions between networks in nature are ordered. Or thirdly, it could be the individual components themselves and thus their properties and how are they diverse is something that contributes to the stability of networks. This aspect is one of the least studied in the context of this paradox, and this is what I specialize in. So in my network models, in mathematical computations, I study the effect of diversity in nodes and see how that affects network stability. In the example of the food web, the diversity of nodes would mean that a carnivore and a herbivore have different roles to play in the network structure, behavior, and stability. Or even two carnivores, let's say a lion and a wolf, have different amounts of effect on the network stability. So I try to encode this in my mathematical models and see if I get closer to the answer of how large ecological networks maintain their stability. Some possible implications of this research are in trying to avoid species extinctions by human interventions in ecological management efforts, or to understand how diversity of individuals still lets the community behave in a certain way, let it be the flocking of birds or the synchronous flashing of fireflies or any other kind of community behavior. So I hope to understand more about community behaviors and how diversity of individuals affects them. And in general, like I said before, we use the similar mathematical framework with a few different assumptions to study different networks. This might have implications to study the effect of perturbations onto the stability of many other kinds of networks. So with my research, I hope to understand how nature maintains large and complex networks, learn something from them, and use this knowledge to help maintain and control the stability of other networks, be them natural or technological. Thank you.